Hello, this is Michelle Miller, and I am going to do a little recording here on the trickier parts of the symbio disease exploring epidemiology simulation. So I'm going to share my screen here that shows the SimuText. And so this is after you have gone through section one. So this is actually page 19 in section one. So let me make sure that this goes a little bit bigger. Yes. Okay, so this is page 19 out of 23 in section one. And you have this formula right here, which talks about the reproduction rate of the microbe that is causing the disease. And so this has to do with the population size, the transmission rate, and then the infectious period. So S is actually the population size. So the tricky part here when I was doing it was the realization that I actually needed to use a calculator to calculate these. So you just times 400 by 0.002 by 3, and then that gives you this. And so if I did that, then this gives me a R sub 0 of 2.4. And then I run the simulation with that R sub 0. And so what you're going to see here is that you're going to see the total number of cases. And so notice that it has stopped here and there's no increase. And so then I can stop that. And then I can plot that. So that is a data point. And so what you want to do is you want to figure out how to manipulate these variables. These would be your independent variables, your independent variable. And then what we're actually measuring is the total number of cases, which is our dependent variable. So if I take this down to my population size is only 200, then that gives me, if I calculate that out using my calculator, that gives me 1.2. So then I put that in here, 1.2, and then I hit run the simulation. And then you'll notice that my cases are much smaller. So that has to do with like how crowded your population is. So then I can stop that again, and then I hit plot again. And so what we're looking for is a value in this next part that what is the minimum R sub 0 value for a disease to spread throughout a population. So that was the first tricky one that took me a while to figure out. Then in section two, so I'm just going to go to section two. This has to do with other types of diseases, including smallpox and measles. And so I discovered that there was a little bit of a interesting problem on page 4. So this is section 2 and page 4. So the trick here is that I need to calculate the number of cases divided by this population size. So as the population size increases, the number of cases might increase, but it's like the proportion that gets sick. And then I'm going to change my vaccination rate. So I can change that vaccination rate to 60% of the population becomes vaccinated. So that would be like if we discovered a vaccine for the COVID virus. And then what I'm interested in is the number of cases over the total population as it relates to the proportion that are vaccinated. So like how many vaccinations would I need to have? And so I can run that simulation and notice that my number of size of cases is increasing and then it stops. So 176. So my population started at 200. And so this would be 176 divided by 200. So this would be 0.88. And then my proportion vaccinated is 0.6. And so then I plot that, and that gives me a value. I can then change my vaccination rate to like, let's say we go up to 80% vaccination rate. And so then I hit start. And notice here, I'm waiting for my total epidemic size cases to stop increasing. So it takes a while. Okay, so it looks like 31 is the total number of cases. And so then what I am going to do is I'm going to take my total number of individuals, which started here at 100, and I'm going to divide it by 32. And so that would be 0.32, 0.32, 32, and my vaccination rate is 0.8. And so then I'm going to plot that. And I'm going to keep doing that until I get to a point where there are no more cases. And so what does my vaccination rate have to be for there to be no more cases? Okay, so then this is for smallpox, so then I can go and answer the questions about measles. So I need to fast forward here for a few. So I can do the exact same thing with measles. And what I can do here, notice that I'm on smallpox. If I click over here, then I'm on measles. And so I could do the same thing with measles. So I could say that my proportion vaccinated is 80%. And then I could run that for measles. And you'll notice here that they have this, the total population size, which is 100. So it's 92 divided by 100. So even with 80% vaccinated, I need 0.9, I still have 92% of the population gets sick. So then I would plot that. And so this is going to be different for measles versus smallpox. Okay. So then the other thing was this formula right here. So I don't want you to freak out about this formula, but 1 divided by the, this is, remember, the reproductive rate, and then 1 minus that. And so this is a critical threshold. So this is the minimum proportion of the population that must have immunity in order for the whole population to be protected from the virus or from whatever is causing a person to be sick. And so this is what they're talking about online about herd immunity. And so if I go to 0.3, I can come up here and I can see that that is over 60%. So I could actually calculate this. If my R sub 0 is 3, then I just take 1 divided by 3 and then minus 1. And that gives me 0.66. And so that is the proportion of the population that must be vaccinated in order to achieve herd immunity. So for me, those were the trickiest. And so you kind of have to remember this formula when you get to the graded questions and the other formulas. But you can always go back to those before submitting your graded questions. So thank you for watching, and I hope that this helps with the more difficult questions in this SimuText simulation.